Okay, so we're going to evaluate expressions. By that I mean what we're going to do is write a program that will take an expression, like the one we see there, and will convert that into its value, that is 14 here. But that's not the only way of doing expression evaluation. This is a direct way of doing it, the obvious way, but also, I mean, we're familiar with this from standard computing programming languages, we can do it in two steps. We could choose to compile it to machine code for a particular sort of virtual machine and then execute those results. And so what we'll do in this section and the next, run through those two different sorts of evaluation, those two different sorts of computation. What we'll do in this section, though, is concentrate on the former. We'll look at evaluation, direct evaluation of expressions. So what we're doing in an evaluation is turning an expression into a number. And so we can write a spec for that function eval. It takes an expression and gives us back an integer. And we can be guided by the type that we wrote earlier on for expressions. And what we can do is build the template for extra evaluation just like this. So we have a case for a number, case for an addition, case for a multiplication. So how do we go about filling in those? Well, the first case, we have the expression represents a number. And what's its value? Well, the answer is it's the number itself. So that's a simple case to fill in. What about for an addition? We have two expressions, the left-hand side and the right-hand side, which each represent a number. And the whole expression is built up by combining those with a plus. How do we find the value of that? Well, what we better do is find the value of the thing on the left, the value of the thing on the right, and then add them together. That's precisely what we write. And then finally, exactly the same thing for multiplication. Find the value of the thing on the left, value of the sub-expression on the right, and multiply those two together. And there we've got that third clause. And now you can see this in action, if you like, on our example expression. We can animate what's going on. We can work out a value for each of the leaves. Each number has its corresponding value. And then we can combine the 3 and the 4 by multiplying them together to get 12. And then at the top, we get the addition of the 2 on the left and the 12 on the right to give us 14. So there you can see the recursion is allowing the values to flow up the tree like that. Okay, so that's it. That's it, except that we missed out one of the cases in our definition. What if I try to evaluate an expression like this? 2 plus 3 times a. What value does that have? I don't know, because I don't know what value a has. So what do I do with this? Well, the answer is I have to add to my evaluator some data structure, something that gives me the value for any variables that are inside my expression. And I do that by adding an environment, I call it, which combines variables, which are atoms, with integers, which are their values. So for example, you can see that we have an environment which gives a the value 23 and v the value 17. So we can say, if I give a this value and v this value, what's the value of an expression that has an a and a v in it? So what I have to do is take the expression, the evaluator I wrote before. You can see that illustrated in blue on the slide. And what I have to do is refactor it to add this extra argument. The extra argument is of type env, and it's an extra argument through the whole of the function. We have to pass that extra argument in to the recursive calls, and we have to add a new clause. So let's just run through the 4 cases again. What we have now is that the value of a number is unchanged. We don't need the environment for that. We pass it in, but in fact we're not going to use it. The second clause is the one which is a new clause, and it says what to do when we have a variable. And the answer is we look up the value of the variable in the environment. I've not said how we're going to do that. We'll do that on the next slide. But we're postponing that, but we're saying we're able to look that value up. And then finally, we have to say what to do about evaluating additions and multiplications. Well, the idea is exactly the same as before. You evaluate the two subcomponents, two sub-expressions, and then combine their results. But we have to remember to pass that environment down to the left sub-expression and the right sub-expression so that we can calculate the values of variables in those sub-expressions. And then we add, or in the case of the final clause, multiply those results together. So we've got pretty much the same definition with an extra clause, but with that extra environment threaded through the definition. So that's the way we do evaluation. And of course, we're using the workhorse here, the Erlang lists, which we use for all sorts of things. What we need to do is say how we're going to do a lookup on that list. And the answer is, what we do is run through the list. When we find a pair where the first element of the pair matches the atom we're looking for, we return the second element of the pair. Note here that we're able to use repeated variables in patterns. Nice thing about Erlang pattern matching, which isn't the case in other languages like Haskell. So nice feature of Erlang, powerful pattern matching facilities. So in the first case, when we found the value we're looking for, we just return the corresponding variable value. In the second case, we do a recursion and look for the value in the tail of the list. And note that if we hit an empty list, the definition will fail. So we're making the assumption that the variable will be defined in the environment. If it isn't, we fail, and the person who's called the evaluation in that case has to deal with the consequences of that function call failing. So what we've seen here is evaluation of expressions where maybe they are constant expressions, we don't need an environment, but where they contain variables, we need to pass in an environment which allows us to look up values of variables and feed those into the expression evaluation. And just to note, again, we saw that the pattern of the recursion here, we have the 4 cases, one for each different kind of expression, and we have recursion in precisely the cases where the type definition is recursive. So that concludes what I want to do about direct evaluation, and what I'll do in the next section is talk about how we build an abstract machine for evaluating expressions and how we compile for that abstract machine and how we run the programs.